Hey everybody, hope everybody's doing well. Mr. Stacy here, and with some physical science. I thought we'd do a new topic because we did a bunch of energy before back when we were in school. So waves is what I'm going to work with. Waves are we're going to go over a few things about waves in this video. We'll see some examples. I got a couple of YouTube videos pulled up, a little simulation. Some other things that I'll show you, as well as we'll talk about different types of waves, how we can, like what their anatomy is, different parts of a wave, and some other stuff like that. So firstly, waves we use to model a lot of different types of phenomena. So phenomena just being things we can observe in the physical universe. Some waves are easy for us to see, like you could think of ocean waves or ripples on the surface of the water. Those are some of the most directly available physical waves that we can see and say, yeah, that's a wave. Or maybe a wave traveling through a string or a jump rope if you were to move it up and down or something. But we can use waves to describe lots of other things that don't really look like waves. So just as some examples up here on this slide, we've got here's a model or a picture, a mathematical picture on the top in orange of a light wave, or what we call electromagnetic radiation. So that could be light that we see. That could be radio waves that we use for communication. That's also light. Microwaves, that's also light. Or gamma rays or X-rays, which are much more energetic forms of light, and can all model with waves. And this is kind of a classic picture of a wave. You got this in the picture, some up and down motion of a line, where you have peaks, or we call crests, at the top, and troughs or valleys at the bottom. And the wave is something that's oscillating or moving back and forth, while it also propagates or moves like left to right in this picture through space. Some other examples are, a cool one is the electroencephalogram pictured below. So this is a rendering of like the electrodes that actually go on the outside of someone's head to monitor the electrical activity inside their brain, which can be represented like in this graph down here as changes in voltage in different parts of the brain that can be used for medical diagnoses. Of course, we've got sound over here. Sound is a series of compressions and expansions in the medium, which is the physical stuff that sound waves travel through. So that could be like the air right now. When I'm talking, I'm able to make compressions and expansions in the air molecules between me and the microphone of the computer, that the computer can then digitize and put into a video, and then you can hear it when it plays out of a speaker. And those compressions and expansions of the air, which are basically like shock waves that we're sending through the air when we speak, we can represent those kind of like this picture down here where we've got a bunch of dots clustered together. That would be a compression of the air molecules. And then the parts where the dots are more spaced out are the expansions or rarefactions of those molecules. We can also represent it with the same sort of up and down line down here, which we also graph in mathematics. We call that a sinusoidal curve, kind of like a sine wave. All right, so here's some examples. We can have physical waves that we can see, again, like the ripples on the surface of water or ocean waves, something like that. But then we can also model a lot of other things that don't really look like waves in terms of waves. Sound, for instance, we don't see sound, right? We hear volume and loudness. We hear pitch, a higher note or a lower note, but we can represent it as a wave. I'm going to give you a little demo here in this simulation of some of the main parts of a wave. Essentially, a wave is a disturbance that travels through something physical, like the sound waves travel through air, or sound can travel through water. A disturbance that travels through something physical like that, or it could be a disturbance that travels through just space, like light doesn't need to travel through the air or the water. It can, but light can also travel through the vacuum of space. It's a different type of wave. Here we have a setup with, for some reason, there's a wrench over here for me to grab onto. This looks like a string of Mardi Gras beads, honestly, but it could just, you could imagine these are different, these are like the atoms, the individual atoms of a string or something, and then I'm going to send it flying out the window. So if I make a disturbance in this medium, this string, we will call the medium. It's some physical thing, like an actual string, and if I disturb it, I can send a wave through it. Send a disturbance through the medium. And I can do that a little bit and I get a little bump there that has a little bit of energy, or I could do it a lot and I can get a big bump traveling through that medium, and it means it has a lot of energy. And you could make something move over here. If someone's standing over here at this window and I go whoosh, and they get hit with it, they can feel it. So a wave is a disturbance that travels through a medium, and it carries energy. Now, what I'm doing right now is just sending individual wave pulses. That's what we say. It's just a pulse. Boom, there's a pulse. Boom, there's a pulse. But I could do this continuously by making it move up and down. And this is what we call a traveling wave. Now it's not an individual pulse. It's actually something that's continuously happening. We say it's periodic. It happens over and over again. And I actually have a setting where I can set it to oscillate, which just means move back and forth. And now we get the picture that's more, closely related to the pictures I showed you just earlier of this up and down wavy motion that has crests or peaks at the top and valleys at the bottom. And we can slow this down and we can take a closer look at the wave. One thing I'd like to point out first is that I can change something down here called frequency. And if I increase the frequency, notice that our peaks get closer together. Higher frequency means that this thing that's oscillating is going back and forth more quickly. And so you get these peaks that are closer together. I could decrease the frequency. Oh, that's too low. Let's go down to like this. Yeah, now clearly the peaks are going to be further apart from one another. There's a lower frequency, which actually also corresponds to lower pitch with sound. Higher frequency would be a higher pitch, a higher note. Another thing I can change down here is amplitude. If I increase the amplitude, that means that this wave actually moves further away from this center line. And for physical waves that travel through stuff, that means they have more energy. If I decrease the amplitude, then it's only going to move a little bit above and below that center line. And the amplitude is just a measurement of how far above or how far below that center line the wave is being displaced, or how much of a disturbance there is in the medium. Now I'm going to put it back at whatever it was at, 75, I think. Okay, another thing. The wave, ask yourself, what direction is this wave traveling? All right, it's being generated over here by this oscillating doodad, and the wave's traveling from the left side of the screen to the right, out the window. So that's the direction that the wave is traveling. But take out a trusty ruler here, not just one, and we look at an individual particle in the medium. So like if we just look at an individual bead in this string of Mardi Gras beads, or an individual atom in this string of atoms of this string, notice that any one of these individual beads or atoms is actually just moving up and down. The only reason the wave is traveling left to right is because these beads are attached to one another. So moving one of them causes its partner next to it to also move. And then, of course, once that one's moving, it makes the one next to it move. And then it has one attached to it, so the one to the right of that also moves. And so they stay connected, and the wave is something that travels through the medium, but the actual particles of the medium are not traveling left to right. Frequently, they're just traveling a little bit, maybe up and down or left and right, but they're not traveling all the way across from one end to the other. That's something that's very important about the behavior of a wave. Okay, so there's a little bit about how we can look at the behavior of a wave with our little simulation. I'm going to go to next, sound waves. So here's this picture in the simulation. If we imagine it to be like a string of Mardi Gras beads, this is a physical thing that you could reproduce. You could grab a slinky or a string and start moving it around, and you could make physical waves that you could see, just like waves on the surface of water, like ripples. Okay, but some waves we don't really see. So like sound, why would we think of sound as a wave? Now in the picture from before, so we could model it as like these little compressions and expansions in space, and that's of like air molecules being compressed together and then stretching back out. So we could think of it as a wave like that. But how do we know? I have on here, I just searched online for an online tone generator. So when I press play, it's going to play a 440 hertz. That's the frequency. That's actually how many times per second the speaker is going to move back and forth, and it's going to produce an A natural. If the volume's turned on. Right, so here's a 440 hertz A natural being played. All right, so we hear that as a certain pitch, and let's say if I double the frequency up to 880 hertz, what's it going to sound like? Is this going to be a higher pitch or a lower pitch? Think about it. Higher pitch. And this is actually one octave above the original note I played. It's another A natural, but it's just a higher pitch. As I can actually move this slider and get different frequencies. Lower frequency means lower pitch. That's what we hear. A higher frequency means a higher pitch. And our range of hearing only goes so far. So if I go all the way up to whatever this is going to be, like 20,000 hertz. Yeah, I definitely don't hear that. Right, so we have only a certain range that we can detect as human beings. Otherwise, we need special microphones. And same thing with light. Light waves have frequencies and wavelengths, and we can only see the visible light. We have to have special cameras in order to see things like the infrared waves or the X-rays. All right, so how can we see this as a wave? Let's find my trusty virtual oscilloscope that I just found online. Pretty cool. And I gotta tell it to wake up here. Can we scroll over? No, of course not. That'd be too easy. An oscilloscope is something that measures oscillations or back and forth movements. So I'm having it use live input from my microphone. I'll unfreeze it. And you can see when I'm talking, it is actually picking up how much the microphone is moving. So it's like detecting the audio from my voice. And right now, like talking is a very complex connection of notes and pitches, so you get this kind of crazy looking combination of waves. And if I freeze it while I'm talking, like, see, that doesn't look like a normal wave, like a nice uniform up and down motion, because it's the combination of a lot of different things happening. But if I play a single note, like if I go back to this guy and play 440 hertz A, hey, yo, that's a wave, huh? Pretty cool. Now, we have, again, the same sort of picture from the simulation where I was playing around with that like string of Mardi Gras beads connected to the wrench. But here it's a constant note. So there's a distance between these two peaks. And the closer those peaks are together, the higher the frequency and the shorter the wave length. The length of the wave is going to be from like before it starts to repeat itself again. So from like peak to peak, trough to trough, or every other time it crosses this center x-axis. That would be the length of the wave. So if I have these peaks really close together, I have a higher frequency, which would sound like a higher pitch. Let's go back and let's play the next octave up, 880 hertz. And so our peaks, if frequency is higher frequency is higher pitch, which this is certainly a higher pitch note, then these peaks should be closer together. The birds are chirping in the background. There we go. All right, those are a little bit closer together, and we get a higher pitch. Notice there's a little bit of disturbance because there's a little bit of background noise too. I'll try, I'm just going to keep it live and slide this, the sliding bar here from a really low pitch, which it's probably not going to detect too well. I'll have to turn the volume up. And then watch what happens in the oscilloscope that's graphing the wave as we increase the frequency or increase the pitch. Yikes. So see how those peaks in our oscilloscope that's graphing the wave got closer and closer together. So with certain types of tools, we can actually visualize the wave made by sound, even though it's not a wave that we directly see. Now, of course, it's the same thing with like color. Different colors we see are actually different frequencies, but we don't see that as a wave. We just see different colors. So we can actually model certain things we see in the universe as waves, not just things that physically look like waves. And we can actually do it with a lot of stuff, like even electrons we can model as being waves. Now, a couple things. Pretty much all waves that we talk about are of two main different types. Either they're mechanical waves, meaning they have to travel through something physical. So like sound needs to travel through the air, it needs to travel through the water, it needs to travel through a solid, like it can travel through the table. Sound is a mechanical wave. Other examples would be like ripples in the water or waves on a string, like in this little virtual environment where I showed you like the Mardi Gras beads. That was a wave traveling through something physical. That's a mechanical wave. Some waves do not need to travel through something physical. Electromagnetic waves or light can travel through the emptiness and the vacuum of space. And so all of these examples down here are just different parts of the electromagnetic spectrum, so a different range of light. So visible light is pretty much right in the middle. Infrared is lower energy and a longer wavelength or lower frequency, and microwaves and radio waves are even lower energy than that. And then the high energy, high frequency parts of light are ultraviolet light, which can give us sunburns or damage your skin, X-rays, which have even more energy, and gamma rays, which will just shred organic tissue pretty quick. So all of these can be modeled as waves. Of these mechanical waves, the physical waves that require a physical medium to travel through, we have two types. Longitudinal, or sometimes called pressure waves. These are waves where, like, look at this guy right here. The middle animation is a wave pulse. This could be like the diaphragm of a speaker. A speaker is just something that goes back and forth and moves the air around it. So this could be the diaphragm of a speaker. It moves once and it sends a pulse through the air. Okay, this is an example of a compression or longitudinal wave. Now down here in the bottom animation is like that speaker's diaphragm is doing it constantly back and forth. And so you're getting kind of this standing wave that's moving. And notice that the wave is moving left to right. Watch this arrow that says wave down here. The wave's moving left to right, but an individual particle is also moving left to right. Look at that individual red dot, or any one of these red dots. They're also moving left to right, but they're staying in a small location. They're not traveling all the way from one end to the other. So when individual particles in the medium move parallel to the wave, notice the red dot moves left and right, and the wave is moving left to right. They're moving in a parallel direction. That we call a longitudinal wave. Sound is an example of that type of wave. The other main type of mechanical waves are transverse waves. So just look at these top two animations on the right. Again, the very topmost one is a pulse. So this is just like the example with my bead of Mardi Gras strings and the wrench and moving it up and down. An individual particle moves up and you get a pulse that travels left to right. If you do it constantly, periodically, going up and down, you get that traveling wave. That's like this middle animation. So you look at this one, and the red particle, the individual atom of the string, or the individual bead of the Mardi Gras bead string, moves up and down. But what direction is the wave traveling? The wave is traveling left to right. So the direction that the wave travels and the direction that the individual particle in the medium travels are perpendicular. They're in different directions. The particle moves up and down, but the wave moves left to right. That's what transverse means. A transverse wave is going to have the particle move perpendicular to the wave. And remember, the particle is just like an atom in the string. It's part of the physical medium. There are lots of waves that are actually combinations of these. Seismic waves, there are different types of seismic waves and earthquakes that are a combination. The actual ripples or like ocean waves on the surface of water, there's an animation down here at the bottom, is actually a combination. Sometimes the particles moving longitudinally, left to right, kind of like the actual wave on the surface of the water is. But the particles also moving up and down too. So this is actually a combination. So you can have combinations of these things. But the two main types of waves are mechanical, requiring a physical medium, or electromagnetic, light, that can travel through whatever it wants, the vacuum of space. And then of those mechanical waves, you can have longitudinal, where the particle in the medium moves parallel to the wave, or you could say in the same direction, left to right and left to right. or up and down and up and down. It's just the same direction as the wave's traveling. Or you can have transverse, where the particle in the medium moves perpendicular to the direction of the wave. In this example, the particle moves up and down, the wave moves left to right. We have different parts of our wave. Mentioned them before. The crest would be like the peak or the mountaintop, the highest point above the center line. If I drew a line horizontally straight through the center, the crest would be the highest point. And we say the trough, or the valley, is the lowest point. We use this symbol lambda, the Greek letter lambda for L, to describe or symbolize the wavelength, the length of the wave. So the further apart these two peaks are, or these two troughs are, the further apart they are, the longer the wavelength. And the closer together they are, the shorter the wavelength. And that's symbolized by the letter lambda. Amplitude, just symbolized with a capital A, is how far away from this center line the peak or the trough is. So you're just measuring from like the x equals 0. You're just measuring, or y equals 0. You're measuring from the x-axis down to the lowest point. That would be the amplitude. And for mechanical waves, if that amplitude's bigger, that means more energy. So here, if this is an example down on the bottom right of a mechanical wave, a physical wave traveling through a physical medium, lower amplitude would be low energy, higher amplitude would be higher energy. So if I go back to my oscilloscope and I play something at high volume, you're going to have a huge amplitude. It's got a lot of energy. Lower volume is going to have a lower amplitude, less energy. And a high energy sound wave will destroy stuff. Like, that's what shock waves do. What else we got? One other thing we can say is these terms frequency and period. Frequency is how many of those mountaintops or peaks you see every second. And that's measured in hertz. So when we go back to our tone generator here, this 4,000 hertz, that means that the peaks and troughs are going to be really close together on our wave. And if we have a lower frequency, those are going to be further apart. So it's how many times per second the wave is repeating itself. Period is how long it takes for the wave to complete one full cycle. And these two things are related to one another. What else was going to show you? So one example here of sound being a physical wave, a mechanical wave. We say something mechanical wave requires a physical medium, something physical to travel through. So this is a short video of a bell, like an alarm bell, ringing inside of a jar. And this jar is connected to an air pump, a vacuum pump, that's going to suck all the air out. And we'll notice as the air is being pulled out of this vacuum chamber, pulled out of this jar, it becomes harder to hear the sound of the bell. You can still hear it, and it's not as loud, is it? Now eventually, if you get all the air out of here, the bell's still ringing, but you can't hear it, because in order to hear the sound from the bell has to travel through a physical medium, which in this case is the air, but all the air is being pulled out, so it's just going to be a vacuum. There's nothing for the pressure, there's going to be no pressure waves from the bell ringing, so we're not going to be able to hear it. Now he's going to detach it and let air back in. And there must still be a little air left in there because you can kind of hear it. You can figure out how to turn the valve. And there's air going back into the chamber where the bell is, and now we can hear it again. So there's an example of a mechanical wave requiring a physical medium to travel through. If we take all the air out of there, you're not going to hear the sound. So like in the vacuum of space, you're not going to have any sound waves anywhere. What else we got? Okay, I think the last thing we got here is, I'm going to put a link in the description of these videos. This girl's channel is really good, but this is an example that I did in class with this plate. And so this is essentially an example of how you can use waves to represent stuff that doesn't really look like they're waves necessarily. And so
Hi there.
Whoa.
Did you want to create some cool physics art?
She scared me. Okay. This is the plate that I had in class, and I put sand on it, and then there was what we call a mechanical wave driver, something that oscillates up and down and makes the plate vibrate, and you can get different patterns of sand. So I'm going to turn this down and play it.
Art without having to do any of the design yourself? I thought so. We've got the square plate on the mechanical vibrator, which is plugged into the tone generator. This vibrates the plate at different notes as we change the frequency here. I'll sprinkle a little sand on the plate, and now watch this. Why does this happen? As I tune the plate to vibrate at very specific frequencies, or notes, the sand moves on the plate into beautiful, though unusual, patterns. As I find higher and higher special frequencies, the patterns on the plate get more intricate. How awesome is this? But it does kind of sound like a dying ferret. Why does it happen? The main concept here is resonant modes. Let's back up a little bit to the physics of waves. In physics, a wave is a disturbance traveling through a medium or through space. If I constrain my medium at the other end, the wave reflects back at me. See? Now, if I send continuous waves down the slinky, they also reflect back, and what I get is two waves, one moving away from me and one moving at me. But obviously the rope can't be in both places at once, so as my incoming wave reflects back, I don't see both waves, I see a combination of the two. The waves add when they're on top of each other, and subtract when they're opposing one another. And something crazy is happening. You've got a wave going this way, combined with a wave moving that way, and when they interfere, the result is, as you might expect, a wave that doesn't appear to be moving in any direction. It's standing! This is called a standing wave. And so is this. The places where the wave appears to be not moving at all are called nodes, and the places where they're moving a lot are called antinodes. Now that we've mastered standing waves, let's go back to our square plate. If you look closely, there are places where the plate and the sand are moving a lot, and places here where they're not moving at all. These are nodes, just like the nodes that didn't move on our slinky. Here are the antinodes. And just like we needed specific frequencies to get standing waves on our slinky, the same is true of our plate. These specific frequencies are called resonant modes, and they're caused by waves traveling out from the center, bouncing off the sides, and interfering with each other just right, so we get standing patterns. Also, the higher the frequency, the closer together the nodes, just like the slinky. But now, what if you did this in 3 dimensions? You could have vibrations coming from the sides and from the front and back, and you'd get interference from all of these such that there'd be nodes in mid-air, places where the air is completely unmoving, and you could, hypothetically, place an object there and cause it to levitate. That would be crazy. But it's exactly what researchers from the University of Tokyo and the Nagoya Institute of Technology did. Well, that's all I got. Really, the physics is the cool part. So, stay tuned to see the vibrations on these plates.
Yeah, waves. All right. That's it for this one. Check for the attachment in the assignment with the video for a Google form you can complete for credit. Adios.
One of the great challenges in this world is knowing enough about a subject to think you're right.
Yeah, Neil. Okay.